Hello everyone, welcome to New World of Possibilities with Unreal and Oculus, our dedicated Unreal developer session. My name is Joe Kirchhoff. I've spent over a decade at AAA game studios, and I'm deeply familiar with the day-to-day experience of game development. My personal focus is on bringing positive change to the tools and pipelines that developers need. And my goal at Oculus is to remove as many barriers as possible to help make VR development easier and more enjoyable. Today I'll be talking about improvements and new features added to the Oculus Unreal Engine 4 integration. I have a rundown of iteration time improvements to discuss, several optimizations and bug fixes that you should be aware of, and finally a few useful code samples of commonly requested functionality that developers have asked us about. Afterwards, we'll hear from Steve Smith, the XR lead at Epic Games, on some upcoming changes to Unreal Editor that we can all look forward to. First, a quick announcement. Support for Quest 2 will be officially released in the October release of the Oculus Unreal Editor 4 integration. I hope you're all as excited as I am to get started with it. When speaking to developers, some of the most common feedback that we receive is that testing changes on the device can be a very time-consuming process while iterating. While Unreal Editor provides methods to test changes directly in the editor, the very nature of virtual reality development eventually requires running natively on the device to ensure the application looks and feels correct. Initial iteration improvements were thus targeted at reducing the time required to launch an application directly on the device. After investigating the Android build logic in Unreal Editor to search for improvements that could be made for Quest devices, we found and resolved several issues that could cause Gradle, which is the tool invoked to bundle the application into an APK package, to be run multiple times unnecessarily whenever source code was modified. In one circumstance, Gradle was being invoked even when it was not required at all, and this added significant overhead to the time required to launch the application. Additionally, we adjusted the logic that determines which maps need to be considered whenever scanning assets to cook and upload to the device when launching. This is to prevent building for maps that are completely unrelated to the specific map that's being launched that was opened in the editor. It's important to keep the number of assets referenced and cooked for a map in check, as reducing this cooked asset list will help improve build times and help launch the game faster even in cases where everything is already up to date. Cook on the fly is a launch option that removes the need to cook all reference assets for a map up front altogether before an application can be launched. This is accomplished by establishing a direct network connection between the device and the host development PC. This allows asset load requests from the application to be processed by the PC and cooked on demand and then transferred over the network. At the cost of additional load time overhead, the benefits to using Cook on the Fly are that assets are no longer required to be cooked completely in bulk up front and copied to the device at all. Instead, only the assets which are actively loaded are cooked and transferred. To improve the experience of using Cook on the Fly, a change was made to the Android application start logic on Quest devices. This prevents the normal immediate pause on launch due to the headset not being active. This initial pause was preventing the Cook on the Fly asset loader from running, so no assets would be requested and loaded in the background until the headset was activated by putting it on. Additionally, as Cook on the Fly requires this persistent network connection between the development PC and the device, we added an option when launching to redirect the network traffic using the Android Debug Bridge application. The original intent of this new option was to utilize a wired USB connection to increase transfer bandwidth if you have a fast cable available, such as a USB cable required for using Oculus Link. While the nature of Cook on the Fly network requests made the improvements compared to a fast wireless connection relatively minor, an added benefit is that a device that would have been otherwise unreachable over the standard network connection would now be able to be connected to, and the connection could be established over ADB and be usable for Cook on the Fly. A good example use case of this would be when your development PC is connected to a VPN while working from home and unable to reach other devices on your home network that are also not connected to that VPN. Even after reducing the frequency of Gradle builds, the fact remains that Gradle itself still consumes a non-trivial amount of time to package the application bundle into the APK. Even for a simple project, such as the VR template provided with Unreal Editor, any code modifications require the full Gradle packaging step to be run so that the new library can be packaged and loaded. To help improve the workflow of users editing code, we've added the ability for an application to automatically load compiled libraries from the application's data directory. To make this simpler to use, an option was added to the editor launch settings that automatically skips the Gradle build if the application is already installed. Instead, the .so library file is copied directly to the device into the appropriate directory so that the newer version can be loaded without building and installing a new APK. On average, as you can see from this graph, the test case on the VR template shows a savings of around 2 minutes per launch after making a small code change. Something to be aware of, the manifest change required to enable this is for development builds only. For security reasons, it can only operate if an application is also debuggable, and any application with this feature enabled would be rejected if submitted to the Oculus store. Unreal Editor manages this manifest change for you and only adds it to debuggable development builds to help avoid mistakes. Compiling code itself can still be a very time-consuming process. However, as you're aware, code compilation is broken up into many discrete units of work that can be processed in parallel across multiple cores on your machine. As there's an upper limit to the number of cores that you may have available on your development PC, we've added remote distribution support using FastBuild, which is an open source build system, to Unreal Editor for both the MSVC and Clang toolchains to help users who may not be able to access the other code compilation distribution methods already available. If you're not familiar, remote distribution allows other computers to process work for a build, offloading processes to remote cores beyond your local cores and allow even more work to be done in parallel. For users that have additional computers available on a local network, using remote processing can drastically reduce the time needed to do large compiles. As you can see from this graph, which shows compile times for the Unreal Editor project for a full rebuild, adding additional remote cores can improve total compile time as the number of cores available increases. Please be aware, however, that there is significant network transfer required for using distribution. Compiled object files can be very large, and the network overhead may not make this beneficial for all users, especially if many of us working from home over VPN connections without access to other machines on a local network. While it is possible to set up distribution over VPN, results may vary wildly depending on network conditions. Up next, I have several recent optimization and bug fixes to discuss. First, we found and resolved an issue where the first render frame was delayed until the fourth frame on application start in Quest. The root cause was the first 3 frames were incorrectly assigned the wrong resolution, MSAA level, and pixel format respectively. Each of these frames were then allocating the color and depth eye buffers, which were then immediately discarded because they were created with the wrong settings. Now, these allocations were entirely unnecessary, so each wasted around 120 milliseconds of initial load time each. Now, by ensuring the correct information is now available on the first frame allocations are now used, and that first frame now correctly renders in VR. It's worth noting that you need to enable the MSAA setting in the project settings to ensure that you will see all the benefits of this fix. Previous versions of the Oculus integration forced MSAA on by default because of legacy device support, and this is no longer the case with the latest version. Second, we found several memory optimizations caused by allocating unneeded render textures, which saved over 120 megabytes when using Vulkan on Quest, and 180 megabytes when using Vulkan on Quest 2. There were several texture buffers allocated which were unused. For example, Mobile Multiview previously allocated a separate scene color buffer, while the default 2D scene render target was for both color and depth was allocated and unused while rendering in VR. Now, in the event a 2D render target is required, the first slice of the multi-view target, basically the left eye, is used instead of allocating a separate buffer. Another smaller savings was also found by removing an unused screen resolution size back buffer. And finally, an unused depth eye buffer resolve texture was removed as well. In addition to the memory settings on Quest, as these allocations are entirely based on the eye buffer or screen resolution size, it was very important for us to fix these before Quest 2, as the greater resolution on that device meant more memory would have been wasted. Third, we made a change that causes the splash screen to appear much earlier during application startup. Previously, the splash screen would have appeared right as the initial map started loading, whereas now it will appear as soon as the plugins are initialized. As there's a requirement to show a splash screen within a fixed time of application start, this should help greatly satisfy this requirement, as the splash screen would no longer need to wait for complete engine initialization to occur, as that is a requirement for the map to begin loading. We suggest that if you aren't adding a splash screen in the project configuration, that you now do so, as creating a shell map or using blueprints to show a splash screen requires much of the engine to start up and will delay how early the splash screen can appear. Fourth, earlier this year, we added a dynamic setting for fixed foveated rendering. If you're unfamiliar, fixed foveated rendering is a technique where sections on the sides of the screen in the user peripheral vision on the sides and top and bottom are rendered at a lower resolution than at the center of the screen. This both can reduce GPU load and can increase the resolution of the center eye texture. When using dynamic foveation, instead of manually controlling the desired current level of foveation, you instead set the maximum level that you want your application to possibly use. The operating system then utilizes the dynamic GPU clock system to control the foveation level. First, the system will push the GPU to the highest level without applying any foveation whatsoever, and then several fake GPU levels are added beyond that max, and those levels are translated to the various quality of foveation. So now in Quest 2, it suggests that you use this setting, as it allows the OS to automatically handle differences in performance and power between the devices. To note, currently all legacy applications have dynamic foveation enabled by default to improve visual fidelity on Quest 2 while maintaining existing performance on Quest. Finally, as we are ensuring compatibility for existing apps on Quest 2, we found that there are many arcane ways that applications were attempting to detect which device was in use. To make this easier to manage in the future, we've removed the getDeviceName API and replaced it with getDeviceType, which returns an enum value instead of a string. This should help unify your device checks and prevent any incorrect logic if the underlying device name happens to change for any reason. To help new developers quickly start up a playable experience in VR, we've released a number of new code samples of commonly requested techniques. First, basic locomotion and interactions are necessary for any game, and those would need to be implemented before you could even begin to start prototyping new gameplay mechanics or features. To assist with this, we released a sample project that contains several different locomotion methods you can use as a starting point. These methods include basic teleportation with a third-person avatar, grab and drag, arm swinging, and joystick controls. This sample also includes interactable objects that focus on two-hand manipulation, as we found the complexity of implementing controls using both hands to manipulate an object was worth showcasing. Also newly added is a sample that covers requesting Android permissions. If you're more comfortable with console development compared to mobile, like I am with myself, you may need to search through unfamiliar documentation targeted at mobile developers to learn how to use Android system features. Features such as requesting access to the microphone, for example. While requesting hardware permission from the platform is common for many applications, it can be difficult to accomplish if you don't know where to get started. Finally, we have several samples that visualize various different rendering features. And these can show you how the different settings with these features can affect both visual fidelity and performance and help you better understand the trade-offs. These samples showcase methods to implement performant mirrors and portals, how pre-baked versus dynamic shadows can affect render performance, how to implement color grading, which is a technique to transform scene colors to simulate lighting conditions, and techniques to render legible text in 3D space. Thank you for listening to a summary of the features Oculus has been working on in the Unreal Editor. I hope that these are helpful in making your development experience smoother and much more enjoyable. Here we provided some links to blog posts and documentations that go into a bit more detail about some of the improvements and code samples I mentioned. So please let us know if you found these helpful and if we can provide any additional samples that would help you get started in the future. You are all a part of building the future of VR, and I really just can't wait to see what everyone creates. All right, up next, we'll hear from Steve Smith, the XR lead at Epic Games. Thanks again, everyone.
Thank you, Joe, for an awesome deep dive into the work that you've been doing to drive down the iteration time on the Quest. This is awesome stuff, and I think it's really going to help a ton of people out. So before I dive into the next section, I'll introduce myself. I'm Steve Smith. I'm the XR lead at Epic Games, and the XR team basically works on foundational features in the UE engine for AR and VR specifically. So the world of VR is a very fast-paced sandbox to be playing in, and things are moving fast for sure. The XR team at Epic has been working hard on implementing new features in the engine, as well as improving and refining the existing toolset that we already have. Today, I'll be guiding you through some of the changes that we've made to the engine in recent releases, as well as pulling back the curtain on some of the new features that we'll be working on for the upcoming 4.26 release and beyond. So first off, OpenXR. And before we go any further, I'd like to take a moment to talk about Epic's commitment to this new platform and why we feel it's so vitally important to the XR ecosystem. So any piece of VR hardware is going to require a runtime to drive it. Currently, each vendor has their own VR runtime, and each VR runtime has its own API to expose the features and allow developers to use it. For Unreal Engine, that means that we have to maintain several plugins. So we have to maintain and optimize those plugins. And we've put a lot of work into hiding differences between these various runtimes. So by and large, VR development is plug and play in Unreal, at least for existing devices. Now, when a vendor creates a completely new piece of hardware, they either need to create a new runtime or leverage an existing one. If they create a new runtime, that means that we're going to need a new plugin. Now, that's fine for anything that's in development at the time the plugin comes out, or that's released after the hardware comes out. But what about content that's already shipped? So this is where OpenXR is really going to help us out. By defining a consistent platform for developers and a consistent runtime behavior, it will push the heavy lifting of porting onto the vendors. With OpenXR, you don't need to port your game. The vendor's runtime will effectively do the porting for you. For Unreal, this means that we get just one plugin to maintain, which gives us way more bandwidth to optimize and innovate. Effectively, it gives us a single point of entry to an unbounded ecosystem. We're no longer bound to a specific set of runtimes. So as part of the work around OpenXR, we've refactored the XR input system, and starting in 4.24 with the motion controller key deprecation, and then completed in 4.25 with a complete removal of motion controller keys. So how it works now is we define the physical controller and each button and control on it. We still bind these buttons with actions. This way we don't lose any information by using generic face buttons. We also don't lose the abstraction capability of motion controller keys, because even though we define physical buttons, an OpenXR runtime can emulate them on any other controller. What this means is when a new controller comes along that's supported via OpenXR, the runtime has a better chance of mapping your specified bindings in a reasonable and useful way. And finally, we're also continuing work on support for variable rate shading. So variable rate shading is the D3D12 name for this technology. On Vulkan, it's referred to as using a fragment density map, and Joe talked about that a little bit earlier. So what is this magical thing? So this example image is from NVIDIA's article where they introduced this technology. In a nutshell, variable rate shading allows us to specify how densely we shade pixels in different areas of the frame. Modern GPUs provide native support for this technology in its various forms, and used judiciously, it can have a significant impact on performance. So here's some examples of what that density map shading pattern might look like. So the 1x1 tile is your standard 1-to-1 shading rate, and this is where we've gotten, this is what we've gotten up to now by default, if you're not using this feature. The 2x2 tile is a quarter rate tile, so each group of 2x2 pixels, or 4 pixels, are shaded by the same shader instance. So where a single pixel shader instance would normally cover 1 pixel, now it's covering 4. The 4x4 is, you guessed it, a group of 16 pixels that all get that same shader operation. And you can also specify different rates in horizontal and vertical axes. So you could have 1x2, or 2x1, or 4x2, or 2x4, etc. So we have a pretty great use case for variable rate shading in VR. And here's a refresher on VR optics, just to illustrate the point. So those lenses in your VR headset apply a pretty heavy pincushion distortion to the image on the underlying display. To counter that and to make the rendered scene look correct, the VR runtime is going to apply a barrel distortion step during the composition phase. If we assume a 1-to-1 pixel mapping at the center of the image, of that barrel distortion image, you can see that as you get closer to the edge, pixels are effectively getting squashed together. Effectively, the closer to the edge you get, the more pixel information is lost. So how does variable rate shading help? The image on the right in this slide is the Vulkan fragment density map for the Oculus Quest. In this density map, each texel in this image, in this particular case, applies to a 32 by 32 block of pixels on the render target being drawn to. And that density map is an R8 G8 format texture, so 8-bit red channel, 8-bit green channel, where the red channel dictates sample density in the horizontal axis, and the green channel dictates sample density in the vertical axis. So just eyeballing this, we can see that we're shading at full rate in the center of the image, and then progressively lower rates towards the outsides. And this matches that barrel distortion applied in the compositor. The result, by applying a fragment density map here, we can tell the GPU to apply less detail as we get closer to the edges. There's no visual impact, or barely any perceptual visual impact here, but there is a significant performance impact. So, as Joe mentioned, we already have support for variable rate shading, or fragment density maps, since it's on Vulkan, and that was checked in for the 424 release. We're actually investigating a broader adoption of this technology in the engine. Both fragment density map support and D3D12's variable rate shading and other options. So this is definitely something that we're going to be implementing since the gains are so significant. And we'll release more details as the roadmap for this becomes clearer. And once this tech is in, there's a ton of possibilities for how it can be applied in the future. In the case of VR, we could see even greater gains when combined with eye tracking, for example, where that 5-degree field of view of the fovea means we could shade even more of the frame at lower rates. Outside of that, in general rendering, there's a ton of possibilities too, but those are beyond the scope of this talk. Okay, so now we've caught up with the recent updates that are out in the wild right now in UE4 for VR. Let's dig in a little bit on what's new and exciting in the world of XR for the upcoming 426 release and beyond. So as part of our continued investment in the OpenXR standard, we're introducing these new features for 426 specifically in and around the OpenXR plugin. So first, we're adding platform support for OpenXR in the Oculus Quest. This will be a beta feature for 426, promoted to production ready for the release following that. We've been working very closely with Oculus to bring this online, and we're super excited to see this evolve. Next, we've built a solid first pass at the extensibility interface for our OpenXR plugin. So the idea behind this system is to provide an easy-to-use extensibility mechanism so that third parties can add OpenXR extension support via new plugins available from the UE4 marketplace. These extensions and their supporting plugins allow vendors to continue innovation on their various platforms while having a minimal barrier to entry to getting this functionality supported in the engine. And finally, we've already added extension support for OpenXR for hand and eye tracking. The mobile rendering team has been super busy for the 426 release as well, refining the mobile renderer. A few of the more exciting, at least for XR, features include, first, the pixel projected reflections on mobile. Now, this feature provides a simple planar reflection of the scene from the base pass. It's applied between the base and the translucent passes. Depending on workload and specific platform, performance may be sufficient for mobile VR, but it'll definitely be a very special case. This effect is hard to support for MSAA, and it also increases bandwidth requirements since it requires a resolve of the scene color and depth. To use this feature, create a planar reflection actor and apply the mobile PPR setting. Now, this will work as usual on PC and console, but it'll use PPR on mobile platforms. This feature has been flagged as experimental for 426. Next, the mobile team have added alpha to coverage support for mobile. This will greatly improve the edges of masked primitives on mobile devices. This feature was explicitly added with mobile VR in mind. This feature is enabled by setting mobile MSAA to a level above 1. 4x is optimal. You choose the material for the tree or grass. Make sure it's a masked material, and then enable the use alpha to coverage in the mobile category in settings. This feature is experimental for 426, so definitely should only be used with that in mind, that it's not production ready. We of course welcome feedback on this and other features as we continue to refine and improve the engine. Another thing I'd like to touch on is the UE4 documentation around the AR and VR space. It's definitely diverged significantly from reality over the past year or so, which is definitely a problem. We're putting a ton of effort into a major overhaul of our documentation, from restructuring to make important concepts easy to find, to updating, improving, and clarifying existing content, to adding documentation around the new as yet undocumented features in both the VR and AR spaces. There will be a significant improvement for the 426 release timeframe in our documentation, but we won't be done then. This will be an ongoing initiative to improve the story around our documentation and just keep improving and iterating on it. We're also in the process of revamping the core project templates for AR and VR, simplifying and refining them to give you the best possible starting point for your specific project. Functionality examples and more complex content will now be found in samples, but it'll be easy to pull the various features that you are interested in over to your project to give you an accelerated start on getting things up and running. Finally, we've been working closely with Oculus on new learning courses, which should be available at our online learning portal roundabout now. This wide-ranging learning path consists of 12 courses, each focused on providing comprehensive instruction for developing VR experiences on Unreal Engine. The courses have been built to illustrate problems commonly faced during production, as well as to walk you through how to identify and solve them step by step. By the end of the learning path through these courses, you'll have an immersive, performant darts game with common and some unique mechanics thrown in. We've pulled together industry experts to provide best practices and in-depth instruction to assist you in taking your projects to the next level. These courses are available at the URL on this slide, and they're available in English, Chinese, Korean, and Japanese. And that's a wrap. Thank you so much for listening, and we're super excited to see all the cool new stuff that people are going to come up with in UE4 in the VR space in the future. Definitely keep an eye on our documentation pages for updates and more information, and for questions and issues, make sure to use the Unreal Developer Network. Thank you again.